Imagine falling toward the center of the galaxy. In one version of the universe, you cross an invisible edge, and everything behind you fades to black, and there is no coming back, ever. In another version, you fall and simply never find an edge at all, sinking instead into something dense and silent and full. The strange truth is that from the outside, these two completely different fates look exactly the same, and right now, we cannot tell which one waits at the center of our own galaxy. For 50 years we have called it a black hole, but it has never actually been proven, and a new idea suggests it might be the other thing entirely, a core of the same dark matter that fills the whole universe. So which one are we orbiting tonight? The abyss or the sphere? Get cozy and settle in. Subscribe if you have not, and stay with me, because by the end you may be living somewhere stranger than you think. Let's dive in. Part 1. The Beast at the Center. Right now, without feeling a single thing, you're moving. You're sitting still, or lying still, wherever you happen to be, and yet you're being carried at more than 500,000 miles an hour around something you've never seen and could never see directly. Everything you have ever known is in motion around it. The Earth circles the Sun, and the Sun, with all its planets in tow, sweeps in a long and patient arc around the center of the galaxy. At the focus of that arc, 27,000 light-years away, sits an object so massive that it organizes the motion of hundreds of billions of stars. It is the anchor of the Milky Way. It is the still point the whole great wheel turns around, and we have given it a name that sounds almost gentle for something so enormous. We call it Sagittarius, a star, written with a little asterisk that astronomers read aloud as the word star. For most of the last half-century, the story of this object has been settled, confident, and clean. It is a supermassive black hole. That is the version you have almost certainly heard. It is the version printed in textbooks and repeated in classrooms and reinforced by one of the most celebrated scientific images of the decade. A monster of gravity, millions of times the mass of the Sun, crouched at the center of everything, swallowing light, bending the paths of stars, holding the galaxy in its grip. It is a tidy and a powerful image, and there is a great deal of careful science behind it. But tonight I want to walk you slowly toward the part of the story that rarely makes it into the headline because it changes the way the whole thing feels. Here is the quiet truth that sits underneath all that confidence. It has never actually been proven. Not once. Not by anyone. We have weighed the object with extraordinary precision. We have squeezed our estimate of its size down to something astonishingly small. Those measurements are some of the finest in all of modern astronomy, and I am not going to wave them away. But a black hole, by its very nature, cannot be seen. It gives off no light. Anything that falls past its edge is gone from view forever. Its existence can only ever be inferred from the way it pushes and pulls on the things around it. And inference, no matter how strong, always leaves a door open just a crack. Through that crack, for decades, a small number of stubborn alternative ideas have refused to go away. And now, fresh research has pushed that door open wider than it has been in years. A team of scientists has published a serious, careful, peer-reviewed case that Sagittarius A star may not be a black hole at all. They argue that it might be something stranger, and, in its own way, far more beautiful. A compact core of dark matter, a dense ball of invisible particles held up against collapse by the same quantum rule that keeps the atoms in your own body from crushing themselves into nothing. If they are right, then the thing at the center of our galaxy is a different beast entirely from the one we thought we knew, and it is connected to one of the largest unanswered questions in all of science. I want to be careful and honest with you from the very beginning, because this is not a video about scientists discovering that the black hole was a lie. They have discovered no such thing, and the consensus still points firmly toward a black hole. This is a video about something subtler, and to my mind something more interesting. It is about the gap between what we have been told and what we actually know. It is about how a careful inference can harden, over the years, into a flat certainty that nobody questions, until one day a new idea comes along that fits all the same evidence just as well, and suddenly the familiar sky looks strange again. So let yourself settle in for a moment. Picture the slowness of the motion you are part of right now. The Sun has been alive for around 4.5 billion years, and in all that time it has completed this great loop around the center of the galaxy only about 20 times. We are riding the 20th lap of a journey older than every fossil, every ocean, every continent on Earth. And at the centre of that lap, the thing we're all turning around, the gravitational well that holds the entire structure together, is an object whose true nature is, even now, still an open question. There is something worth pausing on in that before we go any further. We tend to imagine that the big foundational facts about the universe were settled long ago, locked down by people in white coats, and that what remains for science to do is fill in the details at the edges. But that is not really how it works, and the object at the centre of our galaxy is a perfect example. This is not some faint and distant curiosity at the rim of the observable universe. It is the anchor of the galaxy we live in, the most studied dark object in the sky, the subject of a Nobel Prize and the most famous astronomical image of the decade. And its fundamental nature is still genuinely undecided. If the big questions feel like they are all answered, it is only because we do not look closely at the words. When you do look closely, the certainties soften, and the universe becomes a stranger and more open place than the textbooks let on. So I would encourage you as we begin to let go of whatever you think you already know about the centre of the galaxy. Set it down gently. We are going to rebuild the whole picture from the very first clue, piece by piece, and we are going to be honest at every step about the difference between what we have measured and what we have merely assumed. By the time we reach the end, the thing you were sure of at the start may look entirely different, and the strangeness of that, I promise, is a good kind of strangeness, the kind that makes the night sky feel deeper and more alive than it did before. Tonight we are going to close in on that question from a long way out. We are going to follow the whole strange detective story, from the first faint clue picked up almost a century ago, through the measurements that won a Nobel Prize, all the way to the radical new idea that has scientists looking at the centre of the galaxy with fresh eyes. We're going to ask what it would actually mean if the most famous black hole in the sky turned out not to be a black hole at all. And we're going to discover that the answer connects two of the deepest mysteries in physics in a way that, once you see it, is very hard to unsee. But to understand how big a claim that is, and to feel the full weight of it, we first have to go back to the beginning. We have to go back to a time when nobody knew there was anything at the centre of the galaxy at all, and the beginning, as it turns out, was an accident. Part 2. A hiss nobody understood. The story of the centre of our galaxy does not begin with a telescope pointed at the heavens. It begins with a man trying to get rid of an annoying noise. In the early 1930s, an engineer named Carl Jansky was working for Bell Telephone Laboratories in New Jersey. His job was practical and unglamorous. The company was building radio systems to carry telephone calls across the Atlantic, and those signals kept getting drowned out by bursts of static. Somebody had to find out where all that interference was coming from so it could be dealt with. So Jansky built himself an instrument to hunt it down. It was a strange-looking contraption, a long array of metal antennas mounted on a turntable that rolled on a set of wheels taken from a Model T Ford. The local staff nicknamed it the merry-go-round, because Jansky could rotate the whole thing slowly to figure out which direction a given crackle was arriving from. He found the obvious sources quickly enough. There were nearby thunderstorms which produced sharp crashes of static. There were distant thunderstorms whose noise arrived as a softer rumble. But after he had accounted for all the weather, something was left over. There was a third source, a faint and steady hiss that he could not explain. It was not a storm. It did not come and go with the rain. It was always there, a low background murmur, and the strangest thing about it was its timing. The hiss rose to a peak and faded away once every single day, like clockwork, except that the clock was very slightly wrong. That tiny wrongness in the timing was the clue that changed everything, and it is worth slowing down to understand it, because it is genuinely beautiful. If the noise had been coming from the sun, it would have peaked at the same time each day, every 24 hours, in step with day and night. But it did not. The peak arrived about 4 minutes earlier each day. Over weeks those 4 minutes added up, and the timing of the hiss slowly marched around the clock. Jansky realized that the signal was not keeping time with the sun at all. It was keeping time with the stars. It repeated every 23 hours and 56 minutes, which is the length of what astronomers call a sidereal day, the time it takes the Earth to turn once relative to the distant stars rather than relative to the sun. And there is only one reason a signal would do that. Whatever was producing it had to lie far outside our solar system, fixed against the background of the stars themselves, Imagine the quiet of that moment. Picture a young engineer in New Jersey, in the depths of the 1930s, sitting with a pair of headphones pressed to his ears in the cold, listening to a faint hiss that nobody on Earth has ever properly heard before. He turns his great rolling antenna a little at a time, narrowing down the direction, and the hiss swells when the instrument faces one particular patch of sky. It is the direction of the constellation Sagittarius. It is, though he cannot yet know the full meaning of it, the direction of the centre of the Milky Way. He is the first human being to ever detect the object at the core of our galaxy, and he hears it not as a blaze of light or a burst of energy, but as a soft and patient static, the sound of something 27,000 light-years away whispering into a telephone engineer's headphones. He does not know what it is. Nobody does. He simply writes it down, this hiss from the centre of everything, and the world is not quite ready to understand what he has found. To appreciate how strange and lonely that discovery was, you have to understand that nobody had ever thought to listen to the sky and radio before. For all of human history up to that point, astronomy had meant looking, gathering the visible light of the stars with the eye, and later with the lens and the photographic plate. The idea that the universe might be pouring out other kinds of radiation, radio waves and more, that carried their own hidden stories, simply had not occurred to anyone in a practical way. Jansky's hiss was the first hint that the cosmos was speaking in a language we had never tried to hear. He had stumbled onto an entire second window on the universe, and through that window, the very first thing anyone heard was the murmur of the galactic centre. In fact, the world more or less shrugged. Jansky's discovery was reported, and it even made the newspapers briefly, but the tools to follow it up did not really exist yet, and Jansky himself was reassigned to other work. It fell to an amateur, an engineer named Grota Reber, who built a large dish antenna in his own backyard in Illinois, to take the new science seriously through the late 1930s and into the 40s, painstakingly mapping the radio sky almost single-handedly, while the professional astronomers looked elsewhere. It would take the technological leap of the Second World War, which poured resources into radio and radar, to finally turn radio astronomy into a mature field. And only then, with far better instruments, could anyone return to the question Jansky had raised and ask in earnest what exactly was humming at the centre of the galaxy. He had, almost by accident, founded an entire science, the field we now call radio astronomy, the study of the universe through the radio waves it gives off rather than the visible light. But it would take other people and a great deal of time to pick up the thread he had started, and the question of what exactly was hissing from Sagittarius stayed open for a very long time. For decades, nobody could say with any confidence what the source was. Part of the problem was the era. In those years, black holes were still regarded by most physicists as little more than mathematical oddities, peculiar solutions to Einstein's equations that surely had no real counterpart in the actual universe. The idea that gravity could become so concentrated that it closed off a region of space entirely seemed too extreme to be real. So when astronomers tried to imagine what sat at the centre of the galaxy, they reached for more familiar things. Perhaps it was a tightly packed cluster of stars, so dense and so distant that it blurred into a single source. Perhaps it was the glowing wreckage left behind by an ancient exploding star. Perhaps it was great churning clouds of gas, heated and stirred by some unknown engine. The possibilities buzzed around the scientific community for years, and none of them could be ruled in or out. It was not until 1974, more than 40 years after Jansky's hiss, that the source was finally pinned down as a single compact object. Two astronomers, Bruce Ballack and Robert Brown, using a newer generation of radio instruments, were able to show that the radio emission from the galactic centre came not from a broad smear, but from a remarkably small and concentrated point. It was Robert Brown who later gave the object the name it still carries today. He called it Sagittarius a star. The A marked it as the brightest radio source in that part of the sky, and the little star, the asterisk, was borrowed from the language of physics, where it is used to denote something in a special excited state. The name has a quiet poetry to it that has only grown with time, a star that is not a star, marking a thing we still cannot fully explain. By the time the object had a name, the theoretical ground beneath physics had shifted dramatically. Through the 1960s and 70s, the mathematics of black holes had matured from a curiosity into a serious framework, and the wider scientific community had begun to accept that these objects might genuinely exist out in the universe. So it did not take long for people to put two and two together. Here was a small, compact, immensely powerful source of energy sitting at the exact centre of the galaxy. Here was a new and growing confidence that black holes were real. The suspicion grew, quietly at first and then with increasing force, that the thing humming at the centre of the Milky Way might be a black hole, and not a small one. It might be a black hole of truly gargantuan size. But a suspicion is not a measurement. To turn that hunch into something solid, astronomers needed to actually weigh the thing. They needed to find out how much mass was sitting at the centre and how tightly it was packed. And to do that, they would need to watch, with almost impossible precision, the way the nearest stars moved as they fell under its spell. That is where the next chapter begins, and it is where the invisible first started to give itself away. Part 3. The Stars That Move Too Fast. To weigh something you cannot see, you watch what it does to the things you can. This is one of the oldest and most powerful tricks in all of astronomy, and it is worth holding on to because it sits at the very centre of everything that follows tonight. We cannot see Sagittarius A star. We never have. But we can see the stars that live near it, and we can watch how they move. And the way an object moves under gravity tells you with great precision about the mass that is pulling on it. A gentle, lazy orbit means a modest pull. A violent, racing orbit means something enormous and concentrated nearby. The stars are like leaves caught in a current. You cannot see the water, but if you watch the leaves spin and rush, you can map the river that carries them. For most of the 20th century, this trick could not be applied to the galactic centre, for a simple and frustrating reason. The centre of the Milky Way is hidden behind enormous clouds of interstellar dust, thick veils of gas and grit that lie between us and the core. In ordinary visible light, the kind your eyes use, the centre of the galaxy is almost completely blocked from view. It is like trying to read a sign through dense fog. But as the decades passed, astronomers developed new ways to see through that fog, particularly using infrared light, which slips through dust far more easily than visible light does. And beginning in the 1990s, telescopes finally became sharp enough and clever enough to pick out individual stars in the crowded, dust-shrouded core and to track their motion year after year. The breakthrough that made this possible deserves a mention because it is a quiet triumph of human ingenuity. The Earth's atmosphere is constantly churning, and that churning blurs the light of distant stars, which is why stars appear to twinkle, and why ground-based telescopes were long limited in how finely they could resolve anything. To track individual stars whipping around the galactic centre, astronomers needed to defeat that blur, and they did it with a technology called adaptive optics, in which a telescope's mirror is flexed and reshaped hundreds of times a second by computer, in real time, to cancel out the distortion of the atmosphere. Combined with infrared cameras that could see through the dust, adaptive optics turned the smeared glow of the galactic centre into a field of sharp, individual stars whose motion could be followed year after year. Without that technology, none of what follows would have been possible. We were able to weigh the invisible only because we learned to hold the shimmering sky perfectly still. Two teams, working independently and in a kind of friendly rivalry that drove both to extraordinary precision, led this effort. One was based in Germany, led by the astronomer Reinhard Genzel at the Max Planck Institute. The other was based in California, led by the astronomer Andrea Ghez at the University of California in Los Angeles. Both teams pointed the most powerful telescopes available at the exact centre of the galaxy, and both began the painstaking work of photographing the same tiny patch of sky over and over, year after year, watching how the handful of stars closest to Sagittarius A star drifted and shifted against the background. These particular stars became known as the S stars, and the paths they traced became some of the most precisely mapped orbits in the entire history of science. What those orbits revealed was, frankly, hard to believe. The S stars are not drifting gently. They are moving at speeds that should not be possible for stars, screaming around an apparently empty point in space as if held by an invisible cord. Consider one star in particular, the one astronomers labelled S2, which has become the most famous of them all. S2 completes a full orbit around Sagittarius A star once every 16 years, just under, and at the closest point in its loop it reaches a speed of around 24,000 kilometres every second. Let that number settle for a moment, because it is almost impossible to feel. 24,000 kilometres per second is roughly 8% of the speed of light. It is a single star moving fast enough to cross the entire width of the Earth in under a second, fast enough that the strange effects of Einstein's relativity start to show up in its light. That speed is so extreme that it does something almost no other star can do for us. It lets us watch Einstein's predictions play out in real time. When S2 swung through its closest approach to Sagittarius A star, astronomers detected that the star's light had been subtly stretched toward the red, drained of a little energy as it climbed up out of the intense gravity near the central object. This effect, called gravitational redshift, is a direct prediction of general relativity. The idea that gravity itself slows time and saps the energy of escaping light, and S2 displayed it on cue. They also watched the whole orbit slowly pivot, the long axis of the ellipse rotating a little with each pass, another effect relativity demands near a heavy mass. So the S-stars are not only weighing the invisible object, they are confirming again and again that the gravity around it behaves exactly as Einstein's theory says it should, which is part of why the black hole interpretation feels so natural to so many. The gravity is textbook. It is only the deeper nature of the source that remains in shadow. To really feel how extreme that is, compare it to home. Our own sun is also in orbit around the centre of the galaxy, the same centre, the same Sagittarius A star. But the sun sits far out in the quiet suburbs, 27,000 light-years from the core, and it ambles around its enormous orbit at a stately pace, taking more than 200 million years to complete a single lap. The S-stars, packed in close to the centre, are not ambling, they are sprinting. S2 finishes its loop in 16 years while the Sun needs 200 million. The difference between those two numbers is the difference between standing at the calm edge of a whirlpool and being caught in the screaming centre of it. And the only thing that could whip a massive star around that fast, in a loop that tight, is a truly colossal amount of mass crammed into a truly tiny space. I want you to picture this slowly, because it is one of the most extraordinary sights the universe has to offer, even though no human eye will ever see it directly. Imagine you're standing on some imagined world, far from Earth, somewhere in the crowded inner regions of the galaxy, close enough to look directly toward the centre. The sky here is nothing like the sky you know. It is not a scattering of distant points against black. It is a wall of stars, thousands upon thousands of them, packed so densely that they wash together into a glowing haze, a brightness that never fully fades even in the depth of night. And near the middle of all that light, there is a place where your eye keeps slipping. A patch of apparent emptiness, a spot where there should be something and there is nothing. You watch it. And then you see a star fall. It comes in from the side, a brilliant point of light, and as it approaches that empty patch it begins to accelerate faster and faster until it is tearing across the sky so quickly that you can actually watch it move against the background in a single sitting. And it is bending. The star curves through a long, tight arc, whipping around the empty place, around a hole in the starfield where your eye finds no object at all, and then it flings back out the other side and begins the long climb away. There is nothing at the focus of that curve, nothing you can see, and yet something is there, something weighing 4 million times as much as the Sun, reaching out across the emptiness and bending the path of a massive star as though it were a stone on the end of a string. The star slows and turns and falls back in, and the thing that holds it gives back not a single photon of light. You are watching the most powerful object in the galaxy by watching the one thing it cannot hide, which is its grip. By tracking the S-stars in exactly this way, over years and then decades, the two teams could do something remarkable. They could calculate from the shape and speed of those orbits both how much mass had to be sitting at the centre and how small the region containing it had to be. The mass came out to about 4.3 million times the mass of our Sun, and the size, the volume into which all that mass had to be packed, was astonishingly small. The central mass was confined to a region only about 23 to 25 million kilometres across. To give that some scale, that is small enough to fit comfortably inside the orbit of Venus around our own Sun. 4 million suns worth of mass, squeezed into a space smaller than the inner solar system. That result was the thing that closed the case, at least in most astronomers' minds. There is no known way to pack that much mass into that smaller space and have it sit there quietly as anything ordinary. A cluster of stars that dense would quickly tear itself apart or collapse. A cloud of gas would disperse or ignite. The gentle, familiar explanations that people had reached for in the decades before simply could not survive a measurement that precise. Something incredibly massive and incredibly compact was sitting at the center of the galaxy, and the most natural object that fit the description, the one that physicists were by now entirely comfortable with, was a supermassive black hole. The suspicion had become, for all practical purposes, a conclusion, and that conclusion would soon be carried all the way to Stockholm, to the highest honor that science can bestow. But when it got there, something curious happened with the wording. The people handing out the prize chose their words with enormous care, and in that careful wording, hiding in plain sight, was the very gap this whole story turns on. To see it, we have to read a single sentence very, very slowly. Part 4. The Word. The Nobel Committee chose. In the year 2020, the work of those two patient teams was rewarded with the Nobel Prize in Physics. It was by any measure a triumph decades in the making. Reinhard Genzel and Andrea Ghez shared half of the prize between them, honoured for their long and meticulous tracking of the stars at the Galactic Centre, the work that had weighed the invisible object and pinned down its size. The other half of the prize went to the British mathematician and physicist Roger Penrose, and the reason for his inclusion is worth understanding, because it speaks to how seriously the idea of the black hole was now taken. Back in the 1960s, Penrose had done something that changed theoretical physics. He had proven, with rigorous mathematics, that black holes are not some fragile special case that only forms under perfect conditions. He showed that they are an almost unavoidable consequence of Einstein's general theory of relativity. Given enough mass collapsing under its own gravity, the formation of a black hole, complete with a true singularity at its centre, is simply what the equations demand. Collapse to a black hole, Penrose proved, is what gravity does when it is pushed far enough. So the 2020 prize seemed to seal the matter completely. On one side, you had Penrose proving that black holes must exist as a matter of mathematics. On the other side, you had Genzel and Ghez measuring an object at the centre of the galaxy that looked, by every available number, exactly like one. The theory and the observation met in the middle, and the Nobel Committee blessed the union. For most people watching, that was the end of the conversation. The centre of the galaxy was a supermassive black hole, and here was the most prestigious institution in all of science confirming it for the record. What more could anyone ask? But I want us to do something now that almost nobody bothers to do. I want us to read the actual words of the official citation, the formal statement of what the prize was awarded for, and I want us to read them slowly, because the people who write these citations are not careless. They weigh every word. They know the whole world is watching and that the sentence will be quoted for a century. And the sentence they wrote, the reason Genzel and Ghez were honoured, was this. The prize was awarded for the discovery of a supermassive compact object at the centre of our galaxy. Read it again. A supermassive compact object, not a black hole. The phrase is not black hole. It is compact object, and that is not an accident, and it is not a polite hedge, and it is not the committee being shy. It is a precise and deliberate statement of exactly what the measurements had and had not established. Think back to what the S-star orbits actually proved. They proved that something with the mass of around 4 million suns is crammed into a space smaller than the orbit of Venus. That is an enormous and beautiful result, and it is rock solid. But notice what it does not prove. It does not, and it cannot prove that this something is a black hole rather than some other extraordinarily dense object. The orbits tell you about mass and size. They are silent on the question of what the mass is actually made of, or whether it has an edge from which nothing returns. The Nobel Committee understood this perfectly. They knew that a black hole is a very specific thing. It is not just a lot of mass in a small space. It is a region bounded by an event horizon, a one-way surface in space beyond which nothing, not even light, can ever escape, with a singularity at its core where the known laws of physics break down. The S-star measurements do not reveal an event horizon. They do not reveal a singularity. They reveal a tremendous mass in a tiny volume, which is consistent with a black hole, and is also consistent with one or two other strange possibilities that we will come to. So the committee did the honest thing. They honoured the discovery that was actually made, the discovery of a supermassive compact object, and they let the word black hole stay just out of reach, where the evidence had left it. It helps to be precise about what a black hole actually is, because the precision is the whole point. A black hole is not simply a very heavy, very small object. It is something far more radical. It is a region of space where gravity has become so concentrated that it has, in effect, pinched off a piece of the universe. The boundary of that region is the event horizon, and it is not a surface made of any material. It is a surface made of geometry, a line beyond which every possible direction leads inward, so that escape becomes not difficult but impossible, in the same way that travelling into yesterday is impossible. And at the centre, the mathematics of general relativity predicts a singularity, a point where the density becomes infinite, and the known laws of physics simply stop giving sensible answers. That is what the word black hole actually claims. Not just mass in a small space, but an edge of no return and a hole in the bottom of physics itself. Now hold that next to what the S-star orbits measured. The orbits told us there is a great deal of mass in a small region. They said nothing, directly, about an event horizon. They said nothing directly about a singularity. They constrained the mass and the size and left the deeper question of structure untouched. So the gap between supermassive compact object and black hole is not a quibble. It is the gap between what gravity revealed and what gravity by itself can never reveal. The Nobel Committee chose the smaller, truer claim, and left the larger one as the open question it has always been. I find this genuinely moving, and I want to sit with it for a moment, because it changes something about the way the sky feels. Most of us have carried around, probably since childhood, the flat and simple fact that there is a black hole at the centre of our galaxy. We say it the way we say the Earth goes around the Sun, as a thing that is simply known. And here, in the official record of the highest prize in science, is that exact claim being quietly and deliberately declined. Not contradicted, not doubted, just held at a careful distance. The experts did not overstate what they had found. They were more careful than the story that filtered down to the rest of us. And the difference between what was actually measured and what we were all told, that thin and easily missed difference, has been sitting in the public record this entire time, in a single phrase, waiting for anyone who cared to read it slowly. There is a wider lesson hiding in this single phrase, and it is one of the quiet gifts of paying close attention to science. So much of what we carry as settled knowledge reaches us second hand, smoothed and simplified for the telling, with the careful qualifications sanded off along the way. The researcher writes compact object, the textbook writes black hole, the documentary writes the monster at the centre of our galaxy, and by the time it reaches you, the hedge is gone and only the certainty remains. None of the people in that chain are lying. Each is just rounding off, trading a little accuracy for a little clarity. But the roundings accumulate, and what began as a careful, qualified inference arrives in your mind as a hard, simple fact. Learning to notice that, learning to ask what was actually measured underneath the confident summary, is one of the most valuable habits a curious person can develop, and the centre of our galaxy is a perfect place to practice it. It is a strange and slightly dizzying feeling to discover that something you were certain of was always, technically, an inference. It does not mean you were lied to. It does not mean the scientists got it wrong. The black hole really is the best and most natural explanation we have, and most astronomers would bet heavily on it. But betting heavily is not the same as knowing, and a careful inference is not the same as a proof. And somewhere along the way, the careful inference quietly shed its caveats and hardened into a certainty in the public mind. Tonight we are putting those caveats back. We are reading the fine print that the Nobel Committee took such care to write, and once you have read it, you cannot quite unread it. The centre of the galaxy goes back to being a question. Notice too how the careful word actually frees us rather than confines us. If the case were truly closed, if the centre of the galaxy were a proven, settled black hole and nothing more, then there would be nothing left to wonder about and nothing left to discover there. But the word compact object holds the door open on purpose. It is an honest admission that we have found something extraordinary and have not yet fully named it, and an honest admission like that is an invitation. It says, in effect, here is a genuine mystery, still unsolved, sitting at the centre of your own galaxy, and you are alive at the moment when the question is still live. That is a rare and precious thing. Most of the great questions feel as though they were claimed long ago by people now gone. This one is still open, tonight, overhead. So if the orbits of the S-stars only prove that something massive and compact is there, and not specifically that it is a black hole, then the obvious next question is the one we have to ask. Why did almost everyone settle on the black hole anyway? And what exactly is the room left over for it to be something else? To answer that, we need to understand two things. We need to understand why a black hole is, in some sense, impossible to ever fully confirm by looking. And we need to confront a problem so large and so unsolved that it has kept the door open for alternative ideas all along, a problem that most people have never even heard of. The problem of where these monsters come from in the first place. Part 5. Why the door stays open. There is a reason a black hole can never be confirmed simply by looking at it, and the reason is built into what a black hole is. A black hole is, almost by definition, a thing that hides. Its defining feature is the event horizon, the boundary beyond which gravity is so overwhelming that nothing can climb back out. Not matter, not signals, not light itself. Anything that crosses that boundary is severed from the rest of the universe forever, and since the only way we ever learn about anything in space is by catching the light or other radiation it sends us, the interior of a black hole is permanently fundamentally off limits. We cannot photograph it. We cannot probe it. We can only ever stand outside and watch what it does to its surroundings. We can only see what it does, never what it is. That single limitation is the crack through which every alternative idea about Sagittarius A star has always crawled, and it is worth holding on to because it is going to matter enormously later on. This is not a weakness unique to Sagittarius A star, by the way. It is the situation for every black hole we have ever claimed to find. We never see the object itself. We see a star whose orbit betrays an unseen companion. We see gas heated to incandescence as it spirals inward. We see the gravitational waves of two dark masses merging. We see, in the case of M87, light bent into a ring around a central darkness. In every single case, the evidence is the effect, never the thing. This works wonderfully as long as black holes are the only objects that can produce those effects. The entire edifice of black hole astronomy rests quietly on the assumption that nothing else can leave the same fingerprints. And the dark Fermion model is, at its core, a direct challenge to exactly that assumption, a claim that at least one other kind of object can leave fingerprints that look identical. So when astronomers say the center of the galaxy is a black hole, what they really mean is that they have found a tremendous mass in a tiny volume that gives off no light of its own, and that the simplest object matching that description is a black hole. It is a strong argument, but notice that it is an argument from absence and inference, not from direct sight. We infer the black hole the way you might infer a sleeping animal in a dark burrow from the warmth at the entrance and the tracks in the dirt. You have very good reasons to believe something is in there. You have never actually seen it. And there is a second problem, larger and stranger than most people realize, that keeps the door open even wider. It is the question of where supermassive black holes come from in the first place. This sounds like it should be a solved problem, given how confidently we talk about these objects, but it is not. It is, in fact, one of the largest unsolved puzzles in all of astrophysics, and once you understand it, the confident certainty about Sagittarius A star starts to feel a good deal shakier. Here is what we do understand. We understand very well how ordinary black holes form. When a massive star, many times the mass of our Sun, reaches the end of its life and runs out of the nuclear fuel that has been holding it up against its own gravity, its core can collapse. If the star is heavy enough, that collapse does not stop at a dense ball of neutrons. It runs away completely, crushing the core down past every barrier until an event horizon closes around it and a black hole is born. These are called stellar mass black holes, and they typically weigh a few times to a few dozen times the mass of the Sun. This process is understood in fine detail. The signatures are well observed, and by some estimates there may be as many as 1 billion such black holes scattered throughout the Milky Way alone, the dark remnants of stars that died long ago. But Sagittarius A star is not in that category. It is not even close. At 4.3 million times the mass of the Sun, it is hundreds of thousands of times more massive than the heaviest black hole any dying star could ever produce. There simply are no stars large enough to collapse and leave behind a black hole on that scale. The biggest stars we know of top out at a few hundred solar masses, and even those leave behind black holes of at most a few dozen to a few hundred suns. To get to millions, you need something else entirely, some other process, and here the honest answer is that we do not really know what that process is. There are candid ideas, perhaps countless smaller black holes merged together over cosmic time. Perhaps enormous clouds of gas in the early universe collapsed directly into massive seeds without ever forming stars at all. Perhaps there was some runaway feeding frenzy that let an early black hole gorge itself to giant size with impossible speed. Each idea has problems. None has been confirmed. The formation of supermassive black holes remains genuinely, embarrassingly unsolved. The puzzle gets sharper the more carefully you look at it. The problem is not just that supermassive black holes are large, it is that they were already large when the universe was very young. When astronomers look at the most distant quasars, the brilliant beacons powered by feeding supermassive black holes in the early universe, they find black holes of billions of solar masses that existed less than 1 billion years after the Big Bang. There was barely time in those first chapters of cosmic history for the first stars to form and die, let alone for their remnants to merge and feed their way up to billions of suns through any ordinary process. The objects appear almost fully grown, far too soon, as though they skipped the slow climb entirely. Whatever made the giant black holes, it seems to have made them fast and by a route we have not identified. Sit with what that means for a moment. We point at the centre of the galaxy and say, with great confidence, that there is a supermassive black hole there. And in nearly the same breath, if you ask us how a black hole that large could possibly have come to exist, we have to admit that we do not actually know. We are confident about the name while remaining baffled about the origin. And a confident name resting on an unsolved origin is exactly the kind of thing a careful scientist keeps poking at, because that combination, certainty about what it is paired with mystery about where it came from, is often a sign that the picture is not as complete as it looks. Now, you might be thinking about that famous image, the one from 2022, the picture that was splashed across every news outlet and described as the first direct image of our galaxy's black hole. Surely you might think that settles it. We took its photograph, we saw it. And that image deserves real respect, so let me tell you exactly what it is and exactly what it shows, because here too the detail matters more than the headline. The image came from the Event Horizon Telescope, which is not a single instrument, but a planet-spanning network of radio observatories on multiple continents, all linked together and synchronized so precisely that they function as a single telescope nearly the size of the entire Earth. It is one of the most impressive feats of engineering and coordination in the history of astronomy, and the picture it produced of Sagittarius, a star, in 2022 is genuinely a wonder. It shows a bright glowing ring of light surrounding a darker region in the center. The standard description is that we are seeing the shadow of the black hole, the dark silhouette of the event horizon, ringed by the glow of superheated gas swirling around it. But read what the image actually contains rather than the label attached to it. What the Event Horizon Telescope captured is the light of hot gas circling the central object, with that light bent and warped into a ring by the object's intense gravity, and a darker patch in the middle where less light reaches us. That pattern is exactly what a black hole should produce. The trouble is the word exactly hides an assumption. The pattern is what a black hole should produce, but the image cannot tell you on its own that a black hole is the only thing that could produce it. The central darkness is a shadow cast against glowing gas. It is not a photograph of an edge, and it is not a direct picture of an event horizon. The image is fully consistent with a black hole, but consistency is not proof. Once again, the picture narrows the possibilities. It does not close the door. So we are left with a strange and honest situation. We have a tremendous compact mass we cannot see directly. We have a Nobel citation that pointedly says compact object rather than black hole. We have a famous image that is consistent with a black hole but does not prove one. And we have a gaping hole in our understanding of how such a thing could even form. The door is not just ajar. It is standing open, and for years a small number of researchers have been peering through it, asking whether something other than a black hole might fit all of this evidence just as well. For most of that time, their alternatives were exotic and fringe and easy to dismiss. And then, in the early part of 2026, one of those alternatives walked through the open door carrying something the others had never had. It carried hard numbers, and those numbers were very, very hard to argue with. Part 6. The Challenger that arrived in 2026. Because Sagittarius. A star cannot be observed directly, a small family of alternative explanations has survived quietly in the scientific literature for decades, like guests who never quite leave the party. These survivors are strange, and I want to introduce them honestly, because they are not crackpot ideas. They are serious, if speculative, proposals from working physicists, and they have endured for one simple reason. The data has never been able to kill them. As the gentler possibilities, the star clusters and the gas clouds, were eliminated one by the accumulating precision of the S-star measurements, these stranger ideas remained standing because each of them can, in principle, mimic the gravity of a black hole closely enough to survive every test we have so far been able to run. There are three main contenders worth knowing. The first is the boson star. Ordinary matter is made of particles called fermions, but there is another whole family of particles called bosons, which behave very differently and crucially do not mind crowding together. A boson star would be an enormous smooth star-like body built entirely from bosonic particles, held together by gravity but with no hard surface and no event horizon. The second contender is the Grava star, a genuinely bizarre proposal in which the object has an interior filled with something like dark energy, the mysterious pressure that is pushing the universe apart, wrapped in a thin shell of extraordinarily dense matter. The Grava star avoids the troublesome singularity that lurks at the centre of a true black hole by simply not having one. And the third contender, the one that concerns us most tonight, is the compact dark matter core. The idea that the central object is not collapsed star stuff at all, but a dense ball of dark matter, packed to enormous density and held up by its own internal pressure. You might wonder why scientists bother to keep such strange ideas alive at all, when the black hole works so well. The answer goes to the core of how science actually protects itself from error. A theory that can never be challenged is not a strong theory. It is a dogma. The health of a field depends on a minority of careful researchers continually asking whether the dominant picture is really the only one that fits, building the best possible version of the alternatives and testing them honestly against the data. Most of the time, the alternatives lose, and the dominant picture is strengthened precisely because it survived a serious challenge. Occasionally, an alternative turns out to fit better, and the field advances. Either way, the work is essential. The people building dark matter core models are not trying to tear down the black hole out of contrarianism. They are doing the quiet, necessary work of making sure we believe what we believe for good reasons, and not merely out of habit. For years, these ideas lingered in the margins, respected but unproven, kept alive by the simple fact that they could not be excluded. What none of them had ever done, convincingly, was to take the actual observational data, the real measured orbits of real objects at the galactic centre, and show that an alternative model could reproduce them with the same precision as the black hole. That is a much higher bar than simply being possible in principle, and in February of 2026 for the dark matter core idea, that bar was finally cleared. The work came from a team based in Argentina, at the Institute of Astrophysics in La Plata, near Buenos Aires. One of the lead researchers, Valentina Crespi, studies dark matter at the scale of entire galaxies, and together with a group of international collaborators, she set out to do something direct and testable. She took a specific model in which Sagittarius A star is not a black hole, but a dense core of dark matter, and she compared it, head-to-head, statistically, against the genuine observational data. And she did not just use the orbit of the star S2, though she used that too. She also brought in 5 known examples of a peculiar and fascinating class of objects called the G-objects. It is worth being clear about what a comparison like this actually involves, because the word statistical can make it sound dry when it is anything but. What Crespi did was take the long, precise record of where these objects have actually been observed, year after year, as they trace their loops around the centre, and then ask, for each competing model, how well that model can reproduce the real observations. A black hole of a given mass predicts a particular path for S2. A dark matter core of a given size and density predicts its own path. You lay each predicted path against the measured positions, and you measure the mismatch, the tiny gaps between where the model says the object should be and where it was actually seen. The model that fits better is the one whose predicted paths hug the real data more closely. It is, at bottom, an honest and unforgiving contest, decided not by which idea is more appealing, but by which one matches the dots in the sky. The G-objects deserve a moment, because they are wonderfully strange in their own right. They were discovered in the early 2000s, and they sit very close to Sagittarius, a star. The puzzle of them is that they behave like stars, moving on orbits as stars do, but they look like gas, appearing as fuzzy, extended blobs rather than sharp points of light. And the truly odd thing is that they change shape as they move. As a G-object swings in close to Sagittarius, a star, it visibly stretches and distorts, pulled and smeared by the intense gravity at its closest approach, and then it draws back together as it moves away. Astronomers still debate exactly what they are. Perhaps compact clouds of dust, perhaps stars wrapped in thick shrouds of gas. But for our purposes, what matters is this. Any model that wants to challenge the black hole has to reproduce not just the clean orbit of S2, but also the stranger, shape-shifting behavior of these G-objects. It is a demanding test. Crespi's question was precise and fair. Could a dense core of dark matter reproduce the behavior of S2 and the 5 G-objects to the same level of precision as the black hole model? Not roughly, not in the general ballpark, to the same precision. She ran the comparison, and the results, published in the monthly notices of the Royal Astronomical Society, one of the most respected journals in the field, were remarkable. The dark matter core reproduced the orbits with less than 1% difference from the black hole model. Less than 1%. I want to make sure the weight of that lands, because it is easy to let a number like that slide past. What it means, in plain language, is this. With the observational data we currently have, you cannot tell the difference between a dark matter core and a black hole at the centre of our galaxy. You simply cannot. Both produce the same gravitational pull on S2. Both reproduce the strange contortions of the G-objects. Both fit the measured orbits to within the precision of our finest instruments. The two completely different objects, one a bottomless pit of collapsed space with an edge that erases everything, the other a dense sphere of invisible particles with no edge at all, are, as far as the motion of the surrounding stars is concerned, identical twins. The thing we have been so confident about is gravitationally indistinguishable, right now, from something utterly different. It is tempting to hear less than 1% and think of it as a small imperfection, a tiny edge for one model over the other. It is the opposite. The less than 1% is the size of the gap between the two models' predictions, and it is so small that it falls below the precision of our measurements. In other words, the disagreement between the black hole and the dark matter core, in terms of how they move the stars we can watch, is smaller than our ability to detect. The two models do not merely both fit the data, they fit it so similarly that the difference between them is currently invisible. Imagine two suspects in a case whose fingerprints, footprints, and alibis are identical down to the limits of every test the lab can run. You cannot convict one over the other, not because the evidence is weak, but because the evidence cannot tell them apart. That is the situation we are in with the centre of our galaxy. This is the moment the familiar story genuinely cracks open. It is one thing to say, philosophically, that a black hole can never be fully proven. It is another thing entirely to have a serious, peer-reviewed analysis demonstrate that a specific, concrete alternative fits all the data we have just as well. The dark matter core is no longer just a possibility that cannot be ruled out in principle. It is a model that has been put to the test against the best data we have and has passed, matching the reigning champion blow for blow. But here is where the idea becomes more than just another contender, and where it starts to reach towards something genuinely profound. Because Crespi and her collaborators are not only proposing a new answer to the question of what Sagittarius A star is, they are proposing that the very same idea solves a second mystery, one that is far larger than any single object, a mystery that surrounds not just the centre of our galaxy but the entire universe. To understand how a model of the galactic centre could possibly do that, we have to take a step back, away from Sagittarius A star, and look at one of the largest and most stubborn unanswered questions in all of physics. We have to talk about what dark matter actually is. Part 7. The Invisible Majority. Almost everything in the universe is missing. That sounds like an exaggeration, but it is very close to a literal statement of one of the most important discoveries of the last century. When we add up all the matter we can see, every star, every planet, every glowing cloud of gas, every galaxy stretched across the observable universe, we find that it accounts for only a small fraction of the matter that must actually be there. The rest, the overwhelming majority, is something we cannot see at all. We call it dark matter, and the story of how we know it exists is a story of astronomers being forced, again and again, to believe in something invisible because the visible universe simply would not behave without it. The story begins in the 1930s, with an astronomer named Fritz Zwicky. Zwicky was studying a great swarm of galaxies called the Coma Cluster, and he did something simple. He measured how fast the galaxies in the cluster were moving. What he found made no sense. The galaxies were racing around within the cluster at enormous speeds, with relative velocities of more than 2,000 kilometers every second. And that was a problem, because the cluster did not contain nearly enough visible matter to generate the gravity needed to hold galaxies moving that fast. By all the laws of physics, a cluster with that little visible mass and galaxies moving that quickly should have flung itself apart long ago, scattering its galaxies across the void. And yet there it was, intact, held together. Something invisible had to be supplying the extra gravity, some unseen mass far greater than everything that gave off light. Zwicky gave that missing mass a name. He called it dark matter, and for a long time, almost nobody took the idea seriously. The evidence refused to go away, though, and decades later it returned in a form that was even harder to dismiss. Astronomers began measuring how stars move within individual spiral galaxies like our own Milky Way. In a galaxy, you would expect the stars far out at the edge to orbit more slowly than the stars near the bright, crowded centre, in the same way that the outer planets of our solar system orbit the Sun more slowly than the inner ones. But that is not what they found. The stars in the outer regions of galaxies were orbiting just as fast as the inner stars, sometimes faster, far too fast to be held in place by the visible matter alone. Once again, the only way to make the numbers work was to assume that each galaxy is embedded in a great cloud of invisible mass, far more than all its stars combined, providing the extra gravity needed to keep those outer stars from flying off into space. Perhaps the most convincing piece of evidence came from a cosmic collision. There is a famous object called the Bullet Cluster, which is actually two enormous clusters of galaxies that smash through one another. When astronomers studied it, they were able to map two things separately. They mapped where the ordinary visible matter was, mostly hot gas, which they could see glowing in X-rays, and they mapped where the gravity was concentrated, using the way the collision bent the light of more distant galaxies behind it. And the two maps did not line up. The ordinary gas, slowed by the collision, was bunched in the middle, while the bulk of the gravity, the bulk of the mass, had sailed straight through and out the other side, exactly as you would expect, for a kind of matter that barely interacts with anything. The mass and the visible matter had physically separated. It is very hard to explain that with any trick of ordinary physics, and very natural to explain it if most of the mass is some invisible substance that simply passed through the wreck untouched. Today the evidence has piled up from many independent directions, and the conclusion is no longer fringe. It is mainstream, accepted, and central to modern cosmology. Dark matter is real. It appears to make up roughly 85% of all the matter in the universe, and it seems to surround galaxies in enormous, roughly spherical clouds that astronomers call halos. Our own Milky Way is thought to sit inside one of these halos, an immense and diffuse sphere of dark matter that extends far beyond the bright disk of stars we think of as the galaxy, stretching out into the darkness in every direction. The luminous galaxy, the part we can see, is like the visible glow at the centre of something far larger and entirely invisible. And here is the part that should genuinely unsettle you, because it is the central scandal of the whole subject. After nearly a century of knowing that dark matter is there, after measuring its gravity in cluster after cluster and galaxy after galaxy, we still have no idea what it is made of. None. It gives off no light, so we cannot see it. It reflects no light and absorbs no light, so it casts no shadow we can catch. It interacts with ordinary matter, as far as we can tell, only through gravity, which makes it almost ghostly, slipping through everything, felt only by its pull. It has never been directly detected in any laboratory on Earth, despite decades of increasingly sensitive experiments built specifically to catch it. We know it is there. We have no idea what it is. To grasp how much is at stake in this question, it helps to see where dark matter sits in the full accounting of the universe. When cosmologists tally up everything that exists, they find that ordinary matter, the stuff of stars and planets and gas and people, every atom we have ever touched or seen, makes up only about 5% of the total contents of the cosmos. Dark matter accounts for around 27%, more than 5 times as much as everything visible, and the remaining 68% or so is something even more mysterious, a pervasive pressure called dark energy that is pushing the expansion of the universe to accelerate. So the ordinary matter we have spent all of human history studying, the only kind we can see, is a thin froth on the surface of a reality dominated by two enormous unknowns. Dark matter is not a minor correction or a curiosity at the edges. It is most of the solid substance of existence, and we cannot name it. Dark matter also turns out to be the hidden scaffolding on which everything visible is built. In the early universe, it was the gravity of dark matter, clumping together first, that gathered the ordinary gas into the dense pockets where the first stars and galaxies could form. Without it, the cosmos would likely be a thin, structureless haze, with no galaxies, no stars, no planets, and no us. The grand cosmic web of galaxies that astronomers map across the sky, the great filaments and walls and voids, traces the underlying skeleton of dark matter that shaped it all. We owe our very existence to the gravity of a substance whose nature is a complete mystery, which only sharpens the strangeness of not knowing what it is. There are candidates, of course. For a long time, the frontrunner was a hypothetical particle called the WIMP, which stands for Weakly Interacting Massive Particle, a heavy, sluggish particle that would barely notice ordinary matter at all. Another leading candidate is a much lighter hypothetical particle called the axion. Enormous and expensive experiments have been built far underground, shielded from all interference, patiently waiting for the faint tap of a dark matter particle hitting an atom, and they have hunted both WIMPs and axions for decades. There have been tantalizing hints. A paper published in November of 2025 reported a possible faint signal in old data from the Fermi Gamma Ray Telescope, a signal that could be the glow of WIMPs quietly annihilating one another, but the result is contested and far from settled. The fundamental question stands where it has stood for years, stubborn and open. What is the invisible majority of the universe actually made of? The failure to find it directly after all these years is itself worth sitting with, because it has slowly reshaped the whole field. For decades, the WIMP was the favoured candidate, partly for an elegant reason known as the WIMP miracle, the fact that a heavy particle with roughly the properties physicists expected would naturally be produced in the early universe in just about the right amount to be the dark matter. It was a beautiful coincidence, and it drove the construction of ever larger and more sensitive detectors, each one buried far underground and filled with ultra-pure material, each one waiting in the dark for a single dark matter particle to bump into a single atom. And one after another, those experiments have come back empty. No confirmed signal. The most sensitive searches have now ruled out enormous ranges of the properties the WIMP was supposed to have, and many physicists have begun, quietly, to wonder whether they have been looking for the wrong thing entirely. That growing doubt is part of why ideas like the dark fermion, which were set aside long ago, are getting a fresh hearing now. When the frontrunner keeps failing to show up, the field starts looking again at the candidates it once passed over. I want you to notice something about where we have been searching for the answer, because it is going to matter. We have hunted dark matter in old mines far below the surface, in detectors buried beneath mountains to shield them from cosmic rays. We have hunted it in distant galaxy clusters, in the gravitational lensing of faraway light, in the cosmic radiation left over from the birth of the universe. We have looked outward and downward and far away. There is one place we have not seriously thought to look for the answer to what dark matter is, and it is, in hindsight, almost embarrassingly obvious. We have not thought to look at the centre of our own galaxy. We have not thought that the answer might have been at the centre all along. Because this is exactly what the La Plata team is proposing. They are suggesting that the dense object at the galactic centre and the invisible halo wrapped around the whole galaxy are not two separate mysteries but one. And to make that case, they had to revive a very old idea about what dark matter might be, an idea first written down more than half a century ago, an idea built on one of the most fundamental rules in all of quantum mechanics, a rule that is also the reason you cannot put your hand through a solid table. To see how a ball of dark matter could possibly hold itself up against the crushing weight of 4 million suns without collapsing into a black hole, we have to understand that rule, and it turns out to be the same rule that gives the world its solidity. Part 8. The rule that holds matter up. The reason you do not fall through your chair is, at bottom, a rule of quantum mechanics, and that same rule may be the reason there is no black hole at the centre of our galaxy. Let me build this up carefully, because it is the keystone of the entire idea, and it is genuinely elegant once you see it. Start with ordinary matter, the stuff of you and your chair and the ground and the stars, it is built from particles called fermions. The electrons in your atoms are fermions. The protons and neutrons in your atomic nuclei are built from fermions called quarks. Fermions are, in a real sense, the building blocks of all the solid matter in the universe, and fermions obey a strict and famous rule, first written down in the 1920s, called the Pauli exclusion principle. The Pauli exclusion principle says something that sounds almost too simple to be profound. It says that no two identical fermions can occupy the same quantum state at the same time. In plainer terms, two identical fermions cannot be in the exact same place, with the same energy and the same spin, all at once. They refuse. Each one insists on its own distinct state. And this single refusal, this quantum stubbornness, is the reason matter takes up space at all. When you press your hand against a table, the electrons in your hand and the electrons in the table are forbidden from sharing the same states, and so they push back against one another. That resistance, that solidity, the simple fact that one object cannot pass through another, is not really about electric charge in the way people often assume. It is, at its root, the exclusion principle in action. It is the reason you cannot walk through walls. It is the reason a thing can be solid. It is worth pausing on just how strange and counterintuitive this rule is, because we live with its consequences every second without ever noticing. The exclusion principle is not a force in the ordinary sense. Nothing is pushing the fermions apart in the way that two magnets push apart. It is more like a law of cosmic bookkeeping, a rule about what arrangements of the universe are simply allowed to exist. Two identical fermions sharing the exact same state is not merely difficult to arrange. It is forbidden in the same absolute way that a number cannot be both even and odd at once. And out of that abstract-sounding accounting rule comes the entire solidity of the world. The floor beneath you holds your weight because of a rule about quantum states. The fact that matter occupies space at all, that you and the chair cannot melt into the same region, traces back to this one quiet refusal written into the fabric of reality. And the principle does something even more dramatic in the deaths of stars. When a star like our Sun runs out of fuel and its core begins to collapse, the collapse does not always continue forever. Often it is halted, caught and frozen by the exclusion principle itself. As the electrons in the dying core are squeezed closer and closer together, they begin to resist, because they cannot all be forced into the same states, and that resistance creates a powerful outward pressure called degeneracy pressure, a pressure that comes from nothing but the refusal of fermions to share a quantum state. In a white dwarf, the burnt-out corpse of a sun-like star, it is the degeneracy pressure of electrons that holds the star up against its own gravity forever. In a neutron star, an even denser remnant, it is the degeneracy pressure of neutrons doing the same job. In both cases, gravity wants to crush the object down to nothing, and the exclusion principle stands in the way and says no. Matter is held up by its own refusal to be squeezed. Now hold all of that in mind and bring it back to dark matter. The La Plata team proposes that dark matter is made of a particular kind of particle, which they call a dark fermion. As the name suggests, a dark fermion would be a fermion, meaning it obeys the Pauli exclusion principle, just like an electron or a neutron does, but it would be dark, meaning it interacts with the rest of the universe only through gravity and never through light. It would feel no electromagnetic force. It would not shine, would not reflect, would not absorb. It would be utterly invisible, betraying itself only through its gravity, which is exactly the behavior we observe in dark matter. This idea is not new, by the way. It was first proposed by two astrophysicists, Remo Ruffini and Silvano Bonazzola, all the way back in 1969, and it has simmered quietly in the background of physics ever since, never quite proven and never quite abandoned. That is more than half a century of patient survival for an idea, waiting in the wings while the black hole took centre stage. And there is a certain justice in the fact that it was Ruffini, one of the original authors of this fermion idea, who also did some of the foundational work on black holes themselves in those same years. The same generation of physicists that gave us our modern understanding of the black hole also quietly sketched out the alternative and then set it aside, where it waited for the data and the computing power that could finally put it to a real test. Why does a fermion core never become a black hole, even at 4 million solar masses? The answer lies in how the degeneracy pressure scales. As you add more dark fermions and the core grows heavier, gravity grows stronger, but so does the quantum pressure pushing back, and for these particular particles the balance holds at an enormous but finite density, a density high enough to bend light and grip stars but not high enough to pinch off an event horizon. The matter stays as matter. It never crosses the threshold into the runaway collapse that produces a true singularity. There is a kind of dignity in that. Where a black hole represents gravity winning absolutely, crushing everything to a point, the Fermion core represents a standoff, a permanent truce between the inward pull of gravity and the outward insistence of quantum mechanics that no two identical particles will ever share a state. Here is where it all comes together, and it is a genuinely beautiful piece of reasoning. If dark matter is made of dark fermions, then dark matter obeys the exclusion principle, and that means dark matter cannot be infinitely compressed. Pile enough of it together in one place, let gravity try to crush it inward, and the dark fermions will do exactly what the electrons in a white dwarf do. They will refuse to share their states. They will push back. They will generate an enormous degeneracy pressure that resists the collapse, and under the right conditions, this balance, gravity pulling in and quantum pressure pushing out, can produce an ultra-dense, stable object that holds itself up indefinitely. An object that could, in theory, reach a mass comparable to that of a supermassive black hole, a ball of invisible particles 4 million times the mass of the Sun, held up not by any fire or fuel, but by the sheer quantum refusal of its own matter to be crushed. And this is the crucial difference, the thing that makes it a different beast entirely. Such an object, the dark Fermion core, would be incredibly dense enough to bend light and hold stars in orbit and anchor a galaxy, dense enough to look, from the outside, exactly like a supermassive black hole. The group leader at La Plata, Carlos Argüelles, and his collaborators argue that in every way we can currently observe, it would be indistinguishable from one. But it would not be a black hole. It would have no singularity, no point of infinite density where physics breaks down, and most importantly, it would have no event horizon, no edge, no point of no return. It would be a dense, finite, stable sphere all the way through. Let me show you what that difference would actually feel like by taking you on the same journey twice. Imagine falling toward the center of the galaxy. First, fall toward it as the standard story describes, toward a true black hole. You drop inward through the dark, faster and faster, and at some point far out from the center, you cross a boundary you cannot see and cannot feel. There is no wall, no flash, no warning. There is only an invisible surface called the event horizon, and the moment you cross it, your fate is sealed. Behind you, the light of all the stars in the universe stretches and reddens and crowds together into a shrinking circle, and then winks out entirely. Ahead of you lies a single point of infinite density that the mathematics cannot even properly describe, and there is no path, none whatsoever, that leads back out. You are gone from the universe completely. No signal you could ever send, no light, no cry, will ever reach the outside again. The black hole has closed over you like water over a stone. Now fall again, toward the same 4 million solar masses, the same crushing gravity, the same warping of starlight, but this time toward the object the new model proposes. You drop inward through the dark, faster and faster, and you wait for the boundary. And it never comes. There is no event horizon to cross. There is no point of no return. Instead, you pass into an immense and impossibly dense sphere of dark fermions, particle upon particle upon particle, each one refusing, by the deepest rule of quantum mechanics, to share its place with the next, the entire colossal structure holding itself up by nothing more than that refusal. There is no singularity waiting at the bottom. In truth, there is no bottom at all, only denser and denser fullness. Feel the difference between these two falls. One ends in an edge and an erasure. The other ends in a kind of silent, crushing, complete fullness. And here is the strangest part of all. From the outside, watching the stars wheel around it across 27,000 light-years of space, you could not tell which of these two objects you were looking at. They wear the same face. There is a quiet, philosophical weight to that last point that is worth holding for a moment. We are used to thinking that seeing is knowing, that if we could only get a clear enough look at a thing, we would understand what it is. But the two falls show us the limit of that idea. Two objects could be as different as it is possible for two objects to be. One a true severing of space with no return and a singularity at its floor. The other a finite ball of quantum stubborn particles with no edge and no bottom, and yet present the identical face to every instrument we can point at them from the outside. The difference between them is not in what they look like, it is in what they are on the inside where no light from us will ever reach. To tell them apart, we cannot simply look harder. We have to find some single behaviour, some fingerprint that one can produce and the other cannot, and then go hunting for it. Hold that thought, because it is precisely the thread that the end of this story will pull on. So we now have a model that can hold 4 million suns of dark matter up against gravity without becoming a black hole, and that looks identical to a black hole from a distance. That alone would be remarkable. But the dark Fermion idea does something that no other explanation of Sagittarius A star has ever managed to do, something that lifts it from a clever alternative into a genuinely unifying idea. Because these same dark fermions, the ones packed into the dense core at the centre, would not stay locked in the core. They would reach outward, and what they would form, spreading through and beyond the entire galaxy, is something we have already been talking about all night, without realising the two things might be one. Part 9. One object, not two. For the whole of this video so far, we have been talking about two completely separate things, and we have been assuming, without ever questioning it, that they have nothing to do with one another. The first thing is the object at the centre of the galaxy, the 4 million solar mass anchor we have been calling Sagittarius A star. The second thing is the dark matter halo, the enormous invisible sphere of unseen mass that surrounds the entire Milky Way and holds its outer stars from flying away. In every standard picture, in the black hole model and in the boson star model and in the gravastar model, these two things are entirely unrelated. There is the compact object sitting at the centre, made of one kind of stuff, and there is the dark matter halo wrapped around everything, made of some other kind of stuff, and they simply happen to share the same galaxy. Two separate mysteries, two separate problems, two unrelated unknowns that we have always tackled in two separate fields of research. The dark Fermion model does something that none of those other pictures even attempts. It collapses the two into one. Here is the reasoning, and it follows naturally from everything we just built. If dark matter is made of dark fermions, and if those dark fermions can pile up under gravity to form a dense central core held up by their own quantum pressure, then the very same particles would not all be trapped in that core. The dark fermions reach outward. They thin with distance, growing less and less dense the farther you go from the centre, and in doing so they form a great, spreading, roughly spherical cloud around the entire galaxy. And that cloud, that diffuse outer sphere of dark fermions, is precisely the dark matter halo that astronomers already know surrounds the Milky Way. The dense centre and the diffuse outskirts are not two different objects. They are the inner and outer regions of a single continuous structure, made of one kind of particle, governed by one set of rules, reaching seamlessly from the crushing core at the very centre all the way out to the faint and tenuous edges far beyond the visible galaxy. There is a principle in science, often invoked and sometimes abused, that the simplest explanation is usually the best, that you should not multiply your assumptions beyond what is needed. It is usually wielded as an argument for the black hole, on the grounds that black holes are known to exist and dark fermions are not. But notice that the unification cuts the other way on this particular point. The standard picture asks us to accept two separate, unexplained things at once. It asks us to accept a supermassive black hole whose formation we cannot account for, and, entirely separately, a dark matter halo whose composition we cannot identify. Two mysteries, two unknowns, sitting side by side in the same galaxy, treated as unrelated. The dark Fermion model asks us to accept one new kind of particle, and in exchange it dissolves both mysteries together into a single structure. There is a real sense in which that is the more economical idea, not the less. It trades two unknowns for one. I want to make sure the originality of this is clear, because it is the whole reason the people working on it find it so compelling. In every other model of Sagittarius a star, the object at the centre and the dark matter around the galaxy are two distinct structures that have to be explained separately. The black hole is one thing, dark matter is another thing, and connecting them requires extra assumptions. But the dark Fermion model does not connect them with extra assumptions. It says they were never separate in the first place. The thing at the centre of the galaxy and the invisible mass that holds the galaxy together are, quite literally, the same object, seen at its densest point and at its most diffuse. No other hypothesis unifies the galactic centre with the galaxy's dark matter in this way. It takes two of the largest open questions in physics, the nature of Sagittarius A star and the nature of dark matter, and proposes that they have a single shared answer. And once you really absorb what that means, something shifts, and it shifts in a way that brings the whole thing uncomfortably and wonderfully close to home. Let me take you outward for a moment, slowly. Start at the blazing, dense core at the centre of the galaxy, that impossibly concentrated ball of dark fermions weighing 4 million suns. Now pull back. Watch the density fall away as you move outward, the particles spreading thinner and thinner, the structure growing fainter and more diffuse but never truly ending. Keep pulling back, past the inner stars, past the great spiral arms, past the bright disk of the galaxy entirely, out into the enormous halo, and keep going, because the halo reaches far past the visible galaxy, far past the outermost stars, out into what looks like empty space, out to where the sun is, out to where the earth is, out to where you are. If this model is correct, then the dark matter drifting through the room around you right now, the faint and unfelt mass that physics tells us is passing through your body as you listen, is not some separate substance that merely happens to be here. It is the thinnest, outermost wisp of the very same continuous structure whose dense centre is Sagittarius A star. You're not orbiting the object at the galaxy's centre from some safe and distant remove. You're inside it. You're within the faint outer reaches of the same thing whose furious core anchors the whole Milky Way. The monster at the centre of the galaxy would not be over there, 27,000 light-years away, a thing apart. It would be here, in its most rarefied form, passing through the space between your hands, through the chair you're sitting in, through you, gently and invisibly, all the time. Sit with that for a moment, because it does not need to be frightening. Let it be the opposite. For the whole first half of this story, Sagittarius A star has been a distant alien central thing, a remote monster we orbit but stand apart from. And here, in this model, that distance simply dissolves. The centre of the galaxy reaches out and touches everything, including you, and the thing we have spent a century trying to identify, the dark matter that makes up most of the universe, might turn out to be the same thing as the object at the galaxy's centre, and we have been swimming in it the entire time. There is something almost tender in that idea, the notion that the most enormous and mysterious object in our galaxy is not separate from us at all, but reaches out in its faintest form to fill the empty space we live in. And notice how the idea quietly reframes our place in things. We're used to thinking of ourselves as living in the galaxy, the way you live in a house, a small thing inside a large container separate from its walls. This model suggests something closer to living within a single enormous organism, where the dense brain of it burns at the centre and its faint body extends outward to enfold everything, including us, with no real boundary between the part we call the centre and the part we call the halo and the part we call empty space. The sun and the earth would not be objects sitting inside a galaxy that contains a separate dark thing at its middle. They would be motes drifting through the outermost tissue of one continuous structure whose densest point we have spent a century mistaking for a whole. It is a humbler and stranger place to stand than the one we're used to, and there is a quiet beauty in it. Of course, an idea this beautiful is worth nothing in science if it does not survive contact with the evidence. A unifying theory that explains two mysteries with one stroke is exactly the kind of idea that should make us suspicious, precisely because it is so appealing. The universe is under no obligation to be elegant. So the real question, the one that separates a lovely story from a serious scientific contender, is this. Does the model actually fit the data? Not just the data it was designed to explain, but other data, independent data, things it was never built to account for. And this is where the dark fermion idea has been quietly, steadily accumulating support from directions that have nothing to do with Sagittarius A star at all. Part 10. The idea that keeps fitting. A clever model can be tuned to fit the thing it was built to explain. A good model fits things it was never built for, and the dark fermion idea keeps fitting things it was never built for. Consider, first, a mission that has nothing to do with black holes or galactic centres, a mission whose entire purpose is simply to map the motion of the stars. The European Space Agency operates a spacecraft called Gaia, and Gaia has been engaged in one of the most ambitious surveys in the history of astronomy. Its goal is to measure, with extraordinary precision, the positions and motions of more than 1 billion stars across the Milky Way, building the most detailed map ever made of how our galaxy actually moves. And in data released in 2022, Gaia revealed something at the outer edges of the galaxy that nobody quite expected. What Gaia found was a subtle but important change in how the outermost stars are rotating. As you move outward through the galaxy, the speed at which stars orbit the centre does not stay constant all the way out. At the very outer edges, the rotation falls off, drops away more steeply than the standard models had predicted. Astronomers call this feature a Keplerian decline, a name borrowed from the way the planets in our own solar system slow down at greater distances from the Sun. And this gentle drop-off at the galaxy's edge turned out to be a real problem for the conventional picture, because most dark matter models struggle to reproduce it. The usual assumption is that the dark matter halo is fuzzy and smooth, with no clear edge, and a halo like that does not naturally produce the kind of sharp decline that Gaia measured. But a halo made of dark fermions does. Remember the Pauli exclusion principle, the rule that will not let identical fermions crowd into the same state. That same rule that holds the central core up against gravity also shapes the outer halo, and it shapes it in a very particular way. A halo of dark fermions, governed by the exclusion principle, would not fade away into a fuzzy, edgeless smear. It would form a sphere with a sharper, more defined outer boundary than other dark matter candidates predict, a more clearly delineated edge. And a halo with a sharper edge produces exactly the kind of steeper drop-off in rotation that Gaia observed at the outskirts of the galaxy. The same quantum stubbornness that holds the core together gives the halo a crisp boundary, and that boundary matches the data. Gaia, in other words, was not just mapping stars. It was tracing the shape of the invisible mass that governs their motion, and the shape it traced fits the dark fermion model. It is worth appreciating just how hard-won the Gaia measurement is, because it makes the agreement all the more impressive. To detect the gentle slowing of stars at the outermost edge of the galaxy, Gaia has to measure stellar motions so small that they are comparable to watching a coin slide across a table from hundreds of miles away. It does this for more than 1 billion stars at once, building a 3-dimensional map of the galaxy's motion of staggering detail. This was not an instrument built to test theories of dark matter or the nature of Sagittarius A star. It was built to chart the galaxy. And yet, almost incidentally, in the slow falling off of rotation at the galaxy's rim, it laid down a clean, independent test that the dark fermion halo happens to pass and that smoother halo models struggle with. The best evidence in science often arrives this way, sideways, from a measurement made for some entirely different reason, which is exactly why it carries weight. Nobody tuned Gaia to find this. Then there is the famous image again, the one from the Event Horizon Telescope. We talked earlier about how that picture, the bright ring around a central darkness, is consistent with a black hole but does not actually prove one. Now we can say something stronger. In a publication in 2024, Carlos Arguelles and his team did the detailed calculation to find out what a dense dark fermion core would look like if you imaged it with the Event Horizon Telescope. And the answer was that it would look almost exactly like the picture we already have. A core that dense bends light so strongly that it would produce a central region of darkness ringed by a bright glow of lensed light, an image very nearly indistinguishable, with current instruments, from the black hole shadow. As Crespi has described it, the model not only explains the orbits of the stars and the rotation of the galaxy, but it is also consistent with the famous black hole shadow image, because the dense core bends light so strongly that it creates a central darkness surrounded by a bright ring. The very image that was presented to the world as a portrait of the black hole turns out to be just as good a portrait of a dark matter core. And then there is perhaps the most tantalizing connection of all, one that reaches all the way back to the dawn of the universe. The James Webb Space Telescope, the most powerful observatory ever placed in space, has been peering further back in time than any instrument before it, capturing the light of galaxies whose glow has travelled for so long that we're seeing them as they were less than 1 billion years after the Big Bang, in the universe's infancy. And in the centres of some of these very early galaxies, the telescope has found something that has astronomers genuinely stumped. They are calling them little red dots. They appear to be compact, extraordinarily massive objects, weighing hundreds of millions or even billions of times the mass of the Sun, and the problem is that they should not exist yet. How could anything so massive have assembled so quickly in the first scant chapters of cosmic history, when there had barely been time for stars to form and die? It is one of the hardest puzzles in modern cosmology, and since these objects were first discovered, There have been hundreds of papers and nearly as many competing theories trying to account for them. The dark Fermion core fits here too, remarkably well. If supermassive objects can be built directly out of dark matter, held up by quantum pressure rather than assembled from the slow death of generations of stars, then they could have formed far earlier in the history of the universe than any ordinary black hole could. In the dense, hot conditions of the young cosmos, dark fermions could have clumped together into massive compact configurations on their own, without needing any stars to ignite and die first, without needing any seed at all. That would offer an explanation for how such enormous objects could appear so impossibly early, lighting up the cores of galaxies less than 1 billion years after everything began. A model that was designed to explain one object at the centre of one galaxy keeps quietly accounting for things it was never asked to explain, from the rotation of stars at the galaxy's rim to the most famous image in astronomy to mysterious giants glowing at the edge of time. The little red dots deserve a little more attention because they sharpen the timing problem we met earlier into something almost paradoxical. When the James Webb Telescope first turned its eye on the early universe, the expectation was that the first galaxies would be small, faint, and still under construction, the rough beginnings of structure. Instead, in image after image, astronomers kept finding objects that were too big, too bright, and too mature for the brief age of the cosmos at that time. The little red dots are among the most extreme of these surprises, compact and astonishingly massive, glowing in the cores of galaxies that had existed for only a few 100 million years. The conventional explanation, that they are powered by supermassive black holes, runs straight back into the question of how such black holes could have grown so large so fast, the very puzzle we have no settled answer to. The dark Fermion core offers an escape from that bind, because it does not require the slow assembly. A core of dark matter could have condensed early and directly, born large rather than grown large, present almost from the start. Whether that is what the little red dots really are remains entirely open, but the fact that the model has something natural to say about one of the most confounding discoveries of recent years is exactly the kind of unplanned success that makes physicists pay attention. When a single idea reaches across that many independent observations, scientists take notice, because that kind of reach is hard to fake. It is one thing to build a model that fits the data you aimed it at. It is another thing entirely for that same model to keep landing on its feet every time it is thrown at evidence from somewhere new. The dark Fermion core has been doing exactly that, and so you might, at this point, be ready to conclude that the case is made, that the black hole is on its way out, that we were simply wrong about the centre of the galaxy. But that is not where an honest accounting leaves us, and the people who built this model would be the first to stop you. Because for all its elegance and all its reach, the dark Fermion core has not been proven, and it is important now to put the brakes on and to ask the hardest question of all. How would we ever actually know? Part 11. The honest break and the one test that could decide. It would be very easy, after everything we have just walked through, to get swept up and declare that Sagittarius a star is not a black hole. But that is not what the science says, and it is not what the researchers themselves say, and honesty requires that we slow down here and be very clear. The dark Fermion model is a serious, rigorous, fascinating proposal. It fits the data beautifully. It unifies two great mysteries, and it has not been proven, not even close. The work of Crespi and Arguelles and their collaborators has not shown the black hole model to be wrong, and it has not shifted the scientific consensus, which still points, overwhelmingly, towards Sagittarius a star being a supermassive black hole. The researchers are admirably plain about this. What they have shown is narrower and more careful than a revolution. They have shown that a dark Fermion core cannot be ruled out by the data we currently have, and that, given how much it explains, it deserves a serious look. That is the honest claim, and it is a long way from a victory. I want to linger on the honesty of this for a moment, because it is easy, in a story like this, to slide toward the more exciting conclusion, just because it is more exciting. The temptation, once you have heard how elegant the dark Fermion idea is, how it unifies two mysteries and keeps fitting independent data, is to feel that the black hole has been quietly toppled and that the scientists are just being slow to admit it. That feeling is worth resisting because it is not what the evidence supports, and the researchers themselves are the first to say so. Crespi and Arguelles are not claiming victory. They are claiming a draw with the data we have, and arguing that a draw is itself remarkable and deserves attention. There is a real discipline in being the author of a beautiful idea and still saying, out loud and in print, that your idea has not been proven, and that the older explanation may well be the right one. That discipline is exactly what makes their claim worth taking seriously. It is worth dwelling on why the consensus still favours the black hole, because those reasons are good ones. General relativity, Einstein's theory of gravity, predicts that black holes should exist, and that theory has passed every single test ever thrown at it, with flying colours, for more than a century. Black holes are not just a guess, they are a prediction of our best and most thoroughly tested theory of gravity, and we have very strong evidence that black holes are real elsewhere in the universe. We have detected the gravitational waves, the ripples in space itself, produced when distant black holes collide and merge, exactly as relativity predicts. We have imaged the supermassive black hole at the centre of another galaxy, called M87, with the same Event Horizon telescope. Black holes, as a category, are about as well established as anything in modern astrophysics. Consider what we have actually witnessed elsewhere. In 2015, instruments on Earth detected gravitational waves for the first time, the faint stretching and squeezing of space itself produced by two black holes colliding more than 1 billion light-years away. The waveform they recorded matched, with eerie precision, what general relativity predicts for two black holes spiralling together and merging into one. Since then, dozens upon dozens of such mergers have been recorded, building a catalogue of black holes whose behaviour fits the theory beautifully. And the same Event Horizon telescope that imaged Sagittarius. A star first imaged the supermassive black hole at the centre of the galaxy M87, a far larger and more distant monster, producing a ring of light around a central darkness much like our own. The point is that black holes, as a class, are not a fragile hypothesis. They are woven through modern astrophysics, confirmed by multiple independent lines of evidence across the universe. A new claim that one particular object is not a black hole has to swim against that entire current. So when most astronomers weigh a known object, the black hole, against a new object built from a particle that has never once been directly detected, the dark fermion, they reasonably lean toward the thing they already know is real. That is not closed-mindedness. That is sound scientific judgment, the principle that you should not invent a new entity when a known one already does the job. The dark fermion model then sits in a fascinating limbo. It is consistent with all the data. So is the black hole. Both are unproven. The difference between them, the actual physical difference between a bottomless pit with an event horizon and a dense sphere with no edge, is real and enormous, and yet it is, with our current instruments, completely invisible. Both objects pull on the stars the same way. Both bend light the same way. Both cast the same shadow. We are in the strange and genuinely thrilling position of having two utterly different pictures of the same object, fitting every measurement equally well, with no way, today, to tell them apart. But here is the thing about that word today. It will not always be today. And there is, buried in the physics, a way to settle this. There is one signature, one specific fingerprint, that a true black hole would produce, and a dark fermion core could not, and finding it or failing to find it could decide the question for good. Remember what we said near the beginning, the limitation that has haunted this whole story. We can only ever see what the object does, never what it is. We have been saying that as a kind of permanent prison sentence, the unavoidable fact that a black hole hides itself. But there is one loophole, one thing a black hole does that nothing else can imitate, and it has to do with the strangest behaviour of light near an event horizon. Around a true black hole, in the region just outside the event horizon, gravity becomes so extreme that it can bend the path of light into a circle. A ray of light passing close enough can actually be captured into orbit, looping around the black hole one or more times before either falling in or escaping back out. And because light can loop multiple times, an observer looking at a black hole would see not just one ring of light but a series of progressively thinner, sharper rings nested inside one another, each one made of light that has orbited the black hole a different number of times. These are called photon rings, and they are a direct consequence of the event horizon and the extreme space-time around it. They are, in a real sense, the fingerprint of a true black hole. There is a beautiful subtlety to why the photon rings form. The innermost edge of where light can still escape sits at a special distance from a black hole, a boundary sometimes called the photon sphere, where gravity is precisely strong enough to bend a light ray into a perfect circle. Just outside it, light can loop once, or twice, or many times before spiraling away to reach our telescopes, and each extra loop produces another, fainter, sharper ring stacked just inside the last. In principle, the rings continue inward without end, an infinite series of ever thinner rings crowding toward the edge of the shadow, a fingerprint not just of mass but of an event horizon and the warped geometry around it. It is one of the most elegant predictions in all of physics, light made to orbit, and it exists only where gravity has been allowed to run all the way to its extreme. Now, here is why that matters so much for our question. A dark Fermion core would not produce photon rings. It cannot. The photon rings depend on the existence of a region of such extreme gravity, right at the edge of an event horizon, that light can be trapped into orbit and looped around again and again. But the dark Fermion core has no event horizon. Its dark fermions, by the very exclusion principle that holds them up, refuse to be squeezed into the kind of infinitely dense point that would create that trapping region. The core remains a stable, dense sphere rather than a bottomless pit. Light passing close to it would be bent strongly, but it would not be captured into those tight repeating loops. It would bend, and then it would simply fly away. No photon rings. So here at last is a way to tell the two apart. Find the nested photon rings, and you have found a true black hole with its event horizon and its point of no return. Fail to find them, and the case for the dark Fermion core, the dense sphere with no edge, grows enormously stronger. The limitation that we can only see what the object does, never what it is, finally cracks open, because there is one thing that only a true abyss can do to light, and we are learning how to look for it. What makes this test so satisfying, as a way to end a 50-year argument, is that it does not depend on judgment or interpretation, or which model you find more elegant. It is a yes or no question written directly into the light. Either the nested rings are there or they are not. Either gravity near the centre has run to the absolute extreme that traps light into orbit, which only a true event horizon allows, or it has not, in which case the light bends and leaves and the dense horizonless sphere is favoured. There is no room, in that particular measurement, for the kind of ambiguity that has let the two models live side by side for so long. It converts a question that has been settled, until now only by argument and preference, into a question that can be settled by observation. And that is the moment a debate stops being philosophy and becomes science again. The trouble, of course, is that imaging something as fine as a photon ring around Sagittarius A star is at the very edge of what is possible, and it is going to take new instruments, and probably a good deal of time, but the effort is already underway, and that means this question, which has stood open for half a century, finally has a path to an answer. We are no longer simply arguing about interpretations. We are building the tools that could decide the matter and pointing them at the centre of the sky. Part 12. The open centre of the sky. So how, in the end, will we ever know? The answer is that we will build instruments precise enough to see the difference, and the first of them are already being designed. The American Space Agency has been working toward a mission called the Black Hole Explorer, the idea being to launch a new radio telescope into space and link it directly with the next generation of the Event Horizon telescope on the ground. Because the two would be separated by the enormous distance between the Earth and the spacecraft, the combined instrument would behave like a single virtual telescope larger than the entire planet, sharp enough perhaps to resolve the fine structure of light around Sagittarius A star, sharp enough perhaps to look for those telltale photon rings. It is an extraordinary ambition, and it may be decades before it comes to fruition, but it points the way. In the meantime, other instruments are tightening the noose from other directions. In the mountains of Chile, an instrument called the Gravity Interferometer at the Very Large Telescope is being continuously refined, and it is already tracking something exquisite. It is watching the orbit of S2, that fast-moving star, so closely that it can measure the way the orbit slowly shifts and turns over time, a subtle wheeling of the entire ellipse called precession. The exact direction and amount of that shift is sensitive to the precise nature of the mass at the centre, and so it offers yet another way to test one model against another, to squeeze the competing possibilities until one of them breaks. And far from the galactic centre, in laboratories here on Earth, experiments like one called NEON in South Korea are beginning the painstaking hunt for dark matter particles directly, watching for the faint flash of energy that would be released if a passing dark particle ever struck an ordinary one. If experiments like that ever catch a dark fermion in the act, it would transform the whole picture, turning a hypothetical particle into a measured reality, and giving the dark core model the one thing it most lacks, which is direct evidence that its building block exists at all. So the question is not unanswerable, it is simply unanswered, for now. And there is a real difference between those two things, a difference worth holding on to as we draw toward the close. An unanswerable question is a dead end, a wall. An unanswered question is a door, and we are walking toward it. Somewhere in the coming years or decades, an image will form on a screen in some control room, the sharpest picture of the center of our galaxy ever made. And on that image there will either be a series of fine, nested rings of light, the unmistakable fingerprint of a true event horizon, of a real black hole with a real point of no return, or there will not. There will simply be light bending around a dense dark sphere and flying away, the signature of something with no edge at all, a core of the same invisible matter that fills the universe. One image, two possible futures for everything we believe about the center of the sky, and we are building the eyes that will see which one is true. It is worth saying plainly that whichever way this falls, it will be a kind of gift. If the rings appear and the black hole is confirmed, then we will have done something no one has ever done, which is to truly prove by direct observation that a supermassive black hole sits at the center of our galaxy, closing a question that has stood open since Jansky's hiss. The careful word compact object could finally at last become the word black hole, earned rather than assumed. And if the rings do not appear, if the light merely bends and flies away, then we will have discovered something even more extraordinary, that the anchor of our galaxy is not a black hole at all, but a sphere of the universe's most abundant invisible matter, and that the answer to what dark matter is had been waiting at the center of the sky the whole time. There is no disappointing outcome here. There is only a question that has refused to be settled by argument, finally being settled by light. I find it genuinely wonderful that we live at the moment when this is still open. Think about what that actually means. We have mapped the surfaces of distant moons. We have weighed galaxies and measured the age of the universe and detected ripples in space-time from collisions a billion light-years away. And yet, when it comes to the single most important object in our own galaxy, the thing that anchors every star we see, the thing we are all of us quietly orbiting tonight, we do not actually know what it is. The most fundamental question you could possibly ask about the center of your own galaxy, whether it is a hole in the universe or a knot of the universe's most abundant invisible stuff, is still, right now, genuinely open. The line between the known and the unknown does not run through some distant, exotic corner of the cosmos. It runs straight through the center of the sky you live under, and there is one last turn to sit with, before we let the night close in, the strangest and softest of all. We have spent a century hunting for dark matter, sending detectors into mines and mountains, scanning distant clusters, searching the faint radiation left over from the beginning of time, looking everywhere for the invisible majority of the universe. And it is just possible, if the people in La Plata are right, that the answer was at the center all along. That the thing we have been searching for in every far-off place was sitting at the center of our own galaxy the entire time, hidden in plain sight behind the mask of a black hole, and reaching out, in its faintest and most diffuse form, to fill the very space we occupy. We would not have to go anywhere to find dark matter. We would only have to recognize that we have been living inside it and orbiting its dense center all along. It is worth carrying one more thought into the quiet with you, about what this whole story says about certainty itself. We began with the thing everyone knows, a flat and simple fact repeated in classrooms and captions the world over, that there is a black hole at the center of our galaxy, and by walking slowly through the actual evidence, reading the careful words and asking what was truly measured, we found that the simple fact was never quite as simple as it sounded. That is not a cause for cynicism. It is a cause for wonder. It means the universe still has room in it for surprise, that the largest questions are not all closed, that even the anchor of our own galaxy can still turn out to be something we did not expect. A universe whose every answer was already locked down would be a smaller and lonelier place to live in than this one, where the truth about the center of the sky is still being written. Nobody can tell you tonight which answer is the true one. The consensus still leans firmly toward the black hole, and it may yet be proven right. The dark Fermion core may turn out to be a beautiful idea that the universe declines to confirm, or the image may come back without its rings, and we may have to learn to live in a galaxy whose centre is not an abyss, but a sphere of the same stuff that fills the dark between the stars. Either way, the lesson is the same, and it is a quiet and a humbling one. Some of the most fundamental questions in all of existence remain open, even now, even at the centre of our own galaxy, even about the thing we're turning around at this very moment as you lie here in the dark. The universe is not finished telling us what it is, and the place where its largest secrets are still being decided is not somewhere far away. It is directly overhead, 27,000 light-years straight down into the centre of the sky, turning slowly, patiently, and waiting for us to learn how to look,